Hi, welcome back to Mr. Carroll's Classroom. Today we're going to talk about all the details of graphing quadratic functions which form parabolas. So let's go ahead and get started. Okay, so the first thing we're going to do here is we're going to put up our parent function for quadratics, which is our most basic parabola that we can have. And the parent function is y is equal to x squared. Okay, and so let's just see how we get these points here. These main 5 points that I've graphed. First of all, the most important point is this little point in the middle here. We actually call that the vertex, which we'll talk about in a second. But when I plug in 0, that means y is equal to 0 squared, which is just 0. If I go backwards to -1, x is equal to -1, then -1 squared is +1. If I go back 2 to -2, well, -2 squared is +4, so we go up in that direction. And if I step 1 to the right along the x-axis, 1 squared is also +1, and 2 squared is also +4. So you can see that it forms this parabolic shape if we went ahead and filled in all the gaps here. And it is also symmetric. Okay, and we'll talk about that line of symmetry, but in this case it's symmetric over the y-axis, or that vertical line here. Okay, all right. One thing I do want to point out is from the parent function y is equal to x squared, we can easily expand this to our transformation form, also known as the vertex form for quadratics specifically. But anyway, instead of just having y is equal to x squared, well, if I add in all the different types of numbers that I could add or multiply to that, out front I could have a multiplier, we call it a. On the inside with the x, I could have a number that I add or subtract, we call that h. And then on the outside, we could also add or subtract a number as well, we call that k. All right. Technically speaking, there's another little variable in here called b where I could multiply by the x, but we're gonna keep it simple for this particular case. All right, let's continue. So let's talk about all of the points of interest for our parabola. So here I've just put this generic parabola up here. And you can notice that this one is a little bit different from the parent function. In fact, it's shifted over to the right and down. Excuse me. And the reason why I did that is because I wanted it to cross the x-axis, so it would be very clear to see some specific items that we care about when we're graphing parabolas. Not only do we care about them as we graph them, because they're some of our major points that will help us graph these, but also if we're answering real life questions, then a lot of our solutions to real life questions lie on these specific points as well. So first of all, the one thing that I did just talk about is that a parabola is symmetric. Okay, whether it's facing upwards or downwards, it is going to have what we call an axis of symmetry that will run vertically straight through the middle. Okay, so anyways, we call that the axis of symmetry. Also, the most important point on the parabola is called the vertex, which runs or it intersects the axis of symmetry and the parabola. Okay, so it is always going to be at the lowest point of the parabola, or if this was pointed downwards, then it would be at the highest points. The points where the parabola crosses or intersects the x-axis are called its roots. And there are some alternative names for both the vertex and the roots. Let me bring those up. So the roots, you can call those x-intercepts because that's what they are. It's where we cross the x-axis. So we also refer to those as x-intercepts. And the vertex, you can also refer to this point as either the maximum or the minimum of the parabola. In this particular case, it is the minimum because it is the lowest point on this graph. If this parabola was facing downwards, then we would have the vertex would be a maximum. Okay. Now there are actually a couple more pieces to a parabola that are important to us. However, we are not really going to discuss these in this class, but I do want to show you that they do exist and just show you what they are. So let me remove some of these other items and get these out of the way. But there is also something called a focus and we have a formula that we can figure out where this focus is exactly. And we also have this invisible line down here. Well, I guess it's not really invisible. It's a piece of or it's an important piece of a parabola. It's just that it's not a part of the actual solution set or the actual graph. But anyway, this is called the directrix. So both of these are extremely important. The directrix is really has to do with the definition of a parabola, which at one point, once we learn the focus and directrix, we will cover that. But anyway, and the focus also has to do with that. But in real life applications, you do see parabolas all over the place, and I kind of want to show you that the focus is really the most important piece of a parabola in the real world, typically anyways. For example, if you have dish TV, all right, or any types of satellite, how do those work? Well, what happens is signals are being sent, or it's collecting items as they move downwards, all right, and they hit that parabolic shape. And no matter where they hit this, no matter where they hit it, it will always bounce back to the focus. So all of these will end up bouncing towards the focus. And so typically in the real world, at the focus, we have some kind of sensor which is receiving that information and then doing whatever it is we want to do with it. Okay, so but anyways, so there's the directrix and the focus. Both are actually very important, but we're not going to really concentrate on those. We're going to concentrate on number one, the axis of symmetry, which splits this any parabola right down the middle. The vertex, which is the highest or lowest point on that parabola, that also intersects with that axis of symmetry. And also the roots, where it crosses the x-axis. Okay, all right. So let's go ahead and link this to how we see parabolas in algebraic form. So let's go ahead and take a look. Okay, so the first, actually, before I even talk about this, let's go ahead and throw a parabola up here. Basically, just showing this is just a random parabola. Really don't care about the actual this actual function. I just want to show. This is a parabola, and we're just labeling points here just so that way we can refer to them. In this case, anything in yellow is going to refer to the roots. Anything that's pink is going to refer to the axis of symmetry. And anything that's this like orangish red is going to be for the vertex. So there are really three forms that we can have, or main forms that we will ever see a quadratic written in algebraic form. It is going to be standard form, which is ax squared plus bx plus c. We have vertex form, or in other words, the more generic transformation form, which is a times x minus h squared plus k, which you guys already saw that at the very beginning. And then we also have factored form. So we can always factor our quadratics, and I'm just kind of picking variable names here, but I'm going to keep a number or constant number as a. So we have a out front, and then whatever the factors end up being, we'll just very simply call them x minus b times x minus c. These could be slightly more complicated on the inside here, but for simplicity's sake, we're just going to use b and c there. Okay? All right. So given each of these, like, what are some of the advantages and disadvantages if we want to graph from one of these forms? Well, let's first cover standard form. So if you get a quadratic in standard form, ax squared plus bx plus c, then what does that give you, or what's easy to get from there? So, as I said before, in pink we have the axis of symmetry. In this reddish is going to be vertex. The blue is actually going to be like the a value, which kind of tells you the overall shape of the parabola, which we'll talk about in a second. Anything in green is just going to be some extras. Okay. And this one is actually missing yellow. So actually, if it's in standard form, it tells us nothing about the x-intercepts. All right, but anyways, let's cover this. So we do know the quadratic formula, and actually that's what the axis of symmetry is based on. But if you have a quadratic in standard form, ax squared plus bx plus c, then you can figure out the axis of symmetry simply by taking negative b over 2a. And more specifically, it's the line x is equal to negative b over 2a. The axis of symmetry is a line, so it technically is an equation. All right, so once we know the vertex where it splits in the middle, we can actually figure out what once we know the axis of symmetry, we can figure out the vertex by simply plugging in the x value. The x value is the same thing as the axis of symmetry. It is negative b over 2a, and then all we have to do to figure out the y value for the vertex is go ahead and plug that value back into our standard form. Okay, so we can figure out our vertex fairly easily, but it does require some formulas. So remember, axis of symmetry, x is equal to negative b over 2a. Then we can plug that x value in, to get a y and figure out the vertex. The a out front, this a value out front, it does tell us a few different things about a parabola. First of all, if it's positive, then we know that the parabola is going to open up. If it's negative, we know it's going to open downwards. In fact, in this particular case, this a value I know would be negative because it's opening downwards. Also, the value of a, if it's a fraction, I'm just kind of denoting it as 1 over n, but any fraction will do, then that means it's wider than the parent function itself. And if it's some kind of value n, just like a number greater than 1, then it's going to be narrower than the parent function itself. Right? A fraction essentially compresses the graph vertically, and if it's just some kind of whole number that's greater than 1, then it's going to vertically stretch it. And then in green here, this little extra piece is it's easy to find the y-intercept if we are given a quadratic in standard form. Why? Because where the y-intercept is where the x is equal to 0. So when we're in standard form, 2 of the 3 terms have x's in there. So when I plug in 0 for those x's, those terms are going to cancel out, leaving us just with the constant term c. So we can just say that the y-intercept is always going to be 0, c. So there you go. So we get a lot out of the standard form. We have to do some work, right? You have to know that this formula, negative b over 2a, but really once you have that, then you can kind of come up with a lot of these other pieces. The one thing that we do not get, which is really important, is the x-intercepts or the roots. These yellow points here, right? We don't know where this actually crosses, so how would we figure that out? Well, you'd have to transform this into something else. You'd either have to factor it, or you'd have to use the quadratic formula, or complete the square, or whatever. There are various methods for doing that, but either way, it's going to take some work. Okay, let's move on to the next one. So transformation form. So this is definitely going to be the easiest one to graph always, especially if you are very familiar with your parent function, which you should really commit that to memory. As long as you know all of the parent functions for different algebraic graphs, different types of graphs, then you can always follow the exact same rules, meaning h is always going to be a horizontal shift in the opposite direction. K is always going to be a vertical shift in the same direction as the sign, and then A is going to be either a vertical compression or stretching. Sorry about that. And if it's negative, it opens up downwards. Positive opens up upwards. So, but anyways, so given transformation form, what can we do to graph this thing? Well, it actually doesn't give us that as much as you can see from standard form, but it gives us the important pieces, most of the important pieces, easily with no work whatsoever. So straight away, the axis of symmetry is just going to be x is equal to h. Since the parent function is centered around 0, well, h is a horizontal shift, left and right. So we know that the axis of symmetry must shift by h. So it's just x is equal to h. That's it. The vertex is almost even easier. It is just h comma k. So remember, h is just shifting horizontally, while k is shifting vertically. And so the parent function, the vertex is at 0, 0. So we're just shifting it by h and k. That's it. So the new vertex is going to be at h and k. And then we still have the same exact a value out front, and it has the exact same meanings. If it's positive, it opens up. If it's negative, it opens down. If it's a fraction, it's getting compressed vertically. If it's greater than 1, then it's getting stretched vertically. Okay? So how would we get the roots or the x-intercepts? Well, yes, again, you would have to go ahead and transform this in many different ways. A lot of different ways to do that. Okay, you choose essentially. Okay, but it would take work for sure to get those x-intercepts. All right, so yeah, there you go, transformation or vertex form. It's called vertex form for short because it gives you, that vertex form, which is straight away, which is really easy. All right, and then the last form is really going to be factored form, and I'm going to kind of slide onto the side a little bit here. So if this thing's already factored, or if you go ahead and factor it, what information does factored form give you right off the bat? Well, first of all, it straight away gives you the roots, the x-intercepts. So in this case, if my factors were x minus b and x minus c, then the x-intercepts are going to occur at x is equal to b and x is equal to c. Okay, so yeah, that's kind of important, right? We'd have to do no additional work to get those x-intercepts or those roots. And actually, the axis of symmetry is fairly easy to find as well. Why? Because of that symmetric property. If I have the two x-intercepts, then I know exactly halfway in between is gonna be the axis of symmetry. So all I have to do is take the average of the two, b plus c, divided by 2. And a lot of these are going to be simple graphs, so you can actually just kind of look at it and look halfway in the middle, and you're just going to know where the axis of symmetry is. Now, we still don't know where the vertex would be, so we would have to then go ahead and plug in the x value for that axis of symmetry into the function to get our y value to figure out where that vertex is. Okay? And then, of course, we still have a out front, just like all of these, which is going to tell us the exact same types of things. Okay, so there you go. There are our 3 main forms, and there are pros and cons to all of them. If I had to choose, it would be transformation form all the way, for sure. However, that being said, if I wasn't that interested maybe in the graph, maybe I was just interested in the roots, then I'm pretty much just doing algebra at that point, and I would prefer factored form for sure, and if not that, then standard form, because it's easier for me to get to factored form. As opposed to from transformation form. Okay? All right, so there we go. Let's go ahead and practice this. All right, so I have in front of you, let me go ahead and choose a color here to use. I actually have 3 problems, 1, 2, and 3. However, these graphs are actually all identical. These are all the exact same quadratic, the exact same parabola, but they're all in different forms. X squared plus 4x plus 3 is the same as the quantity x plus 2 squared minus 1, which is the same as x plus 1 times the quantity x plus 3. So let's go ahead and graph each one of these in their respective ways. Okay, so let's go ahead and I guess we'll just move from left to right. All right, so first of all, if I was graphing this guy, I'd think about all those clues. Well, first of all, I actually already know the y-intercept, because if I plug in 0 for x, then it's just going to be 3. So I can actually put a point down here at 0, 3. There we go. Actually, let me use a different color so we can see this a little bit better. So there we go. There's 1 point right away. Okay? All right, so what else can I do? Well, I can figure out the axis of symmetry. Remember, the axis of symmetry is x is equal to negative b over 2a. So that's negative 4 over 2a. In this case, a is 1, so it's just 2 times 1, which means that the axis of symmetry is going to be negative 2. So let's go ahead and put that in. And remember, that's not actually a part of the graph, so I'm going to put a dotted line in there. So meaning it's important to us, but it's not actually this part of the solution set. The solution set is going to be the solid line in the end here. All right, where do we go from here? Let's see. Well, I could get the vertex. Let's go ahead and get the vertex by going ahead and plugging in -2 for x. So we'll say the vertex is going to be -2, and if I plug in -2 here, let's see here, that's going to be 4 minus 8, which is -4, and then -4 plus 3 is -1, so there we go. So the vertex is going to be at -2, -1. All right, so I have a lot of information right now, and actually, technically speaking, I could go ahead and sketch this because I know there's the question is this point downwards like that, or is it upwards like this? And I do know it is upwards because it has to go through this point right here. But let's go ahead and be more specific than this terrible drawing that I just did here. Let's go ahead and figure out the x-intercepts. So the only way to do this is going to be, well, I mean, there's another way. You could go ahead and use the quadratic formula, but that's even more lengthy. So we're not going to do that. Let's go ahead and we're going to say 0 is equal to, and we're going to factor this thing. So we're going to do it by guess and check. So I have two binomials starting with x because it's just 1x squared out front. And I need two numbers that are going to multiply to 3 and add to 4. So that's just going to be 3 and 1. All right, and since I have two things multiplied by each other equal to 0, I could set each equal to 0 and solve for x, which in that case, x would be -3 for this one, and x would be -1 for that one. So let's go ahead and plot those. Now we have our x-intercepts. So -1, 2, and 3, and -1. There we go. So we've got 4 points here. I think we are all set to go ahead and graph this thing. Hang on one second. See if I can do a halfway decent graph. I started off pretty good, and then we ended poorly. Yeah. Hang on. Last chance. And we're going to end with this one. We'll say close enough. Okay. All right. So let's go ahead and move on to the next one. So whenever I'm dealing with transformation or vertex form in this case, I am going to do this based off of the parent function, which you should again commit this thing to memory, all of these points. Whoops, having trouble drawing my parabolas today. All right, but anyways, so there's our parent function. So really the question is, how does this thing get shifted left, right, up, down, and is there any vertical stretching or compressing? And straight away, I actually know that there is no vertical compression or stretching, and it's also just facing up because there's a 1 out front here. Okay, A is 1 in this case. So really, it's just about moving this thing left, right, up, and down. So let's go ahead and I'm going to remove these points, and we're going to go ahead and recreate these based on the vertex. So straight away, I can say the vertex is equal to, I'm not even going to do the axis of symmetry because it's just going to run straight through the vertex. But anyway, the vertex is just HK. Now remember, H is always the opposite here, so it's actually -2, and then K is -1. And the reason why that's -2, by the way, is because it's in the formula, it's x minus h. So if I were to get x plus 2, that would have to be x minus -2, and that would turn, that -2 would turn this into an x plus 2. So that's why it's a -2. Okay. So anyways, and that's why it's the opposite actually. All right. So let's go ahead and plop that vertex on here. So -2, -1. So far so good. It's the same as our last one here. But anyways, and actually that's all I need to know. Actually, as long as I know the shape of the parent function, I know that I'm going to go over 1 up 1. And then over 2 up 4, because 2 squared is 4. So over 2 to the right 2, and then up 4. 1, 2, 3, 4. And then it's going to be symmetric the other way. So left 1 up 1, left 2 up 4. And there we go. Very easy to graph. See if I go nice and slow this time so I don't waste all of your time trying to graph a decent parabola. Okay, so there we go. All right, so again, transformation or vertex form, definitely the easiest. All right, next problem here, last one, it's in factored form. So straight away, if I want to figure out the x-intercepts, then I'm interested where y is equal to 0. So I set it equal to 0. X plus 1 times x plus 3. And since two things are multiplied by each other to get 0, I can set them each equal to 0 and then solve. So x plus 1 is equal to 0, solves to x is equal to negative 1. X plus 3 is equal to 0, solves to x is equal to negative 3. So there we go. We've got our, in factored form, we have our x-intercepts very easy. So negative 1 and negative 3. So now the question is, does this thing look like this or does it look like this? We don't really know. Does it look like really wide? Not really. Whoops. Can't see that, can you? Hang on one second. So does it look like really wide? We're not really sure. So we need more information. So the first thing I'm going to do, and really that more information is really the other major piece, which is the vertex. I really want that vertex. So with parabolas, since they are symmetric, I know that the axis of symmetry is going to go straight through the center right in between these 2 points. In other words, the vertex, which has to run through that, is going to be, the x value is going to be negative 2. So now all I have to do is plug negative 2 back into the original, and we will get the y value for our vertex. So if I plug in negative 2, let's see here. Negative 2 plus 1 is negative 1. Negative 2 plus 3 is positive 1. And negative 1 times positive 1 is going to be negative 1. So our vertex is going to be at negative 2, negative 1 right here. And there we go. That is going to be good enough for us, and we can go ahead and graph this. Now, this is a little bit dangerous because we only have 3 points here. It would be better to have 5 points. You really want to have 5 points. So maybe you would plug in, this one right here at x is equal to negative 1, 2, 3, 4, negative 4, and then x is equal to 0 probably to get the y-intercept. But I'm going to go ahead and graph this thing since we already know what it looks like. But really, rule of thumb, if you have the major pieces, that's great, but always try to get 5 points. So if you need a couple more, go ahead and just figure out, just plug in and get a couple more. Okay, so let's go ahead and we're going to do one more problem. This one's going to be slightly harder. And again, this is going to be all the same problem, just in different forms. And so you can see here, this is definitely going to be harder. In fact, all of these I can actually see from the A value, I automatically know that this thing is going to point downwards for all of them. And also, since it's 1/2, it's going to be compressed, meaning it's going to be like widened out a little bit as opposed to narrow. So it's going to be vertically compressed. All right, but the other pieces I don't really know. So let's go ahead and figure those out. So let's start on the left, I guess, again. So the first thing I'm going to do is the y-intercept here. So the y-intercept is, if I plug in 0 for x, then I just get negative 6. So the y-intercept is negative 6, 1, 2, 3, 4, 5, and actually don't even have that many, so we're just going to plug that down here. It's kind of off the graph, but, let's put it there because it does tell us something about it, right? Okay, let's move on here. So let's see here. Let's go ahead and figure out the axis of symmetry. So remember, the axis of symmetry is going to be x is equal to negative b, which is negative 4, all over 2 times a. Well, a is negative 1/2. One second. So that's equal to negative 4, and 2 times negative 1/2 is negative 1. Negative 2 over 2, which is negative 1. And negative 4 over negative 1 is positive 4. So x is equal to 4. So we'll say 1, 2, 3, and 4. So here we go. Here's our axis of symmetry. Pretty far over to the right. All right, but anyways, now we can figure out the vertex of this thing. So if I plug in, say vertex, if I plug in 4, then what do I get? Let's see here. Well, that is 16 times negative 1/2 is negative 8. And then negative 8 plus 16 is positive 8. And then positive 8 minus a 6 is going to be positive 2. So at 4, 2 is going to be our vertex. So 4 and then up 2. Now at this point in time, I actually do know, like I said, it points downwards and it's kind of widened out. Okay, so, let's go ahead and figure out the actual x-intercepts here. Okay, and this is definitely going to kind of go off to the side, so we're probably going to only be able to graph one of these. But anyways, we're definitely going to have to either use the quadratic formula or we can go ahead and factor this thing. So let's go ahead and factor it. And I think what I'm going to do, since it's going to be a little bit more challenging to factor this, is I'm going to kind of do it over here, and then I will just erase it once we're done. But anyway, so yeah, so for x-intercepts, we're going to set it equal to 0. So y is equal to 0. Anyway, so that's equal to negative 1/2 x squared plus 4x minus 6. And let's see here. To make this easy, I really don't like this negative 1/2. So I'm going to multiply both sides by negative 1/2. Now 0 times negative 1/2 is still just 0. Now if I multiply this whole left side by negative 1/2, oh, I'm sorry, not by negative 1/2. I'm sorry, by a negative 2, because I want to wipe out that negative 1/2. So anyways, so negative 2 times negative 1/2 is positive 1 to give me x squared. This is going to be negative 2 times 4x, which is negative 8x. And then negative 2 times 6 is plus 12. All right. So this just became a lot easier for us, right? By taking out that fraction there, by multiplying everything by negative 2. Anyways, so here we go. So we're going to go ahead and we will factor this. And actually, I'm going to go ahead and factor this over here now. So that means that 0 is equal to, now I need two numbers that multiply to get to positive 12 and add to get to negative 8. So that's going to be x minus 2 times x minus 6. And I am going to go ahead and just erase this over here to make room for us for later. But anyways, so I know now that x is equal to positive 2 and x is equal to positive 6. So let's go ahead and graph those. So here we go. So positive 2, and we're pretty close here. Let's see, 1, 2, 3, 4, 5. So it's going to be kind of like slightly off here. And so we can go ahead and connect these dots and graph our parabola. Okay, there we go. All good. Lengthy process there, but we got it done. All right, next up here. Now, even though this has definitely, it's a little bit more challenging for transformation form, we can do it fairly easily. So let's go ahead and first go ahead and take care of the vertex. So the vertex is going to be equal to h, which is 4, comma k, 2. So there we go. So we have 1, 2, 3, 4, up 2. Boom, done. Now, the negative out front. This negative out front does tell me that it's going to be going downwards. Now, normally, let's go ahead and put in, I guess I'll put in some points I'm going to erase here in a second. Now, normally, the parent function, if it was just flipped downwards, it would be over 1 down 1 and then over 2 down 4. 1, 2, 1, 2, 3, 4. Right? 1, 2, 3, 4. Something like right here. But we know that this thing is compressed by 1/2. So what does that mean? Well, so I go over 1, and instead of going down by 1, we're going to go down by half of that. So this, in other words, is going to go over and then down by half. So right here. And then this one here is going to go over 2, but vertically, remember we're compressing vertically, not horizontally, it's only in the vertical. So we go over 2, and then instead of going down 4, we're only going to go down half of that, which is just 2. So instead of going all the way down to here, we're just going to go down to here. Okay? All right, and same thing since it's symmetric over here. So over 1 down 1/2, over 1 down by 2. And at that point, I can go ahead and just get rid of these real quick. These yellow ones, and we will connect the dots. Not bad, right? Definitely a lot easier. Okay, and then the last one here, let's go ahead and we'll graph the same one here. So here with the factors, we are going to go ahead and say 0 for the x-intercepts, or the roots. So 0 is equal to negative 1/2 times x minus 6 times x minus 2. And then you might be thinking, well, what do I do with this 1/2? I'm not used to seeing that in a factor. Well, just divide both sides by negative 1/2, right? Because 0 divided by anything is just 0, right? So you end up with 0 is equal to x minus 6 times x minus 2, which means that our x-intercepts or roots are going to be x is equal to 6 and x is equal to 2. So we can graph those, boom, and around here, boom. All right, now we know directly in between there, so I'm literally just going to visually look at this. So in between here, there's 1, 2, 3, 4. So halfway in between there is 2, and that's going to be our axis of symmetry. So the axis of symmetry is going to be x is equal to 1, 2, 3, 4. And in order to find the vertex, we just need to plug that thing in. So that means the vertex is equal to 4, comma, and let's go ahead and plug that in. So if I plug in 4 minus 6, then that is, let's kind of write this here. So negative 1/2 times 4 minus 6, or negative 2, and then 4 minus 2 is positive 2. So negative 2 times 2 is negative 4, and then negative 4 times negative 1/2 is going to be positive 2. So we know the vertex is at 4, positive 2. So 4 and then up 2. And there we go. We only have 3 points, but that's okay. Normally, though, if you were like taking a test or something like that, you should probably just plug in a couple more points just to get those. Okay. All right, guys. So there we go. There is, let me bring myself back up here. So there is everything really there is to know, I guess, about graphing quadratic functions, at least in relation to all of the basic pieces. The vertex, the axis of symmetry, and your roots. And the rest we can just piece together with whatever information we have. We did not talk about the focus and the directrix, but there is a specific formula that will allow you to calculate exactly where those are at, and those will be in a more advanced lesson in the future. All right, so hopefully you got something out of this lesson, and I'll see you in the next one. Have a good one. Bye now.